and have to cover it now. So this is a model that is a tripartite model. I'll be presenting this at WinterSim this year, and it integrates together the three types of modeling in a single model. It integrates together system dynamics, agent-based, and discrete event model in a single model. Basic conceptual understanding of this is as follows. So the name derives from the fact that people worked on it were four people from northern China, and that means the Northerners model in Chinese. And it is a model which uses system dynamics modeling. So it's a model that characterizes diabetic end-stage renal disease. And fundamentally, there's a system dynamics component that simulates the evolution of most of the population among weight states and up to the point of prediabetes. Okay, so you have three weight states and then prediabetes, and people change weight over time, and some of them eventually go on to develop prediabetes. Now, at the point that someone progresses on to full-blown diabetes, they are then turned into an agent. So they become a set of agents flowing out of this that are diabetics. And because they're agents, we can associate them with very fine-grained information, including historical information about their experience over time. We can, for example, figure out how long a given agent has been on a waiting list, or we can find out the number of transplants that agent has received, the number of times they've switched dialysis modalities, etc. So they're agents after this point. They sort of come out of the system dynamics model, which is most of the population. This is 85% of our population. Really, really very quick to simulate. This 15% is simulated as agents, and some of these go on to develop end-stage renal disease. And those who develop end-stage renal disease will go on to develop to be placed, moreover, not only into this sort of agent-based context, which you'll see here, but they're further placed into, once they start waiting for a kidney transplant, if they're deemed eligible, they will start awaiting arrival of a kidney. And actually, that is captured, I think is it, I'm going to have to go check where that's captured here visually. But there it is. It's in Maine, but further down here to the right. So an individual who's under care, because certain processes like assessment to be placed on a transplant waiting list, and then receiving, so to be placed on an assessment waiting list and then on a transplant waiting list, those waiting lists are dictated by resource availability. And to allow us to capture differential resource availability and availability of doctors and availability of kidneys, we then represented a person as flowing through a discrete event model where their placement on resources is dictated according to resource availability. The most key resource for available is the availability of a kidney. Kidneys become available from deceased donors or living donors for use by others, and individuals who have been on this waiting list, once they progress to the front of the queue, they'll be able to pick up either a living donor kidney or a deceased donor kidney, depending on how their case is being handled. So these individuals who are agents, many of them are also circulating simultaneously within this discrete event model. And much as in this model that we were working with just previously, you have people in the population, and some of them right now are also under care. They're also in this process delivering care to them. So it is with this model. We have these agents, and many of them are also in this process of giving care at various stages being delivered a kidney transplant or being assessed for it, or et cetera. So once they receive a kidney transplant, they exit the system, but they remain an agent, and they're circulating in this system here. I'm going to make this full screen so we could see it a little bit more. There's actually many components to this, and you'll notice that we have individuals in peritoneal and hemodialysis. So I should introduce, once people get budded off as agents, once they leave the system dynamics model and they come in here, they're turned into an agent. They begin at this beginning of the chain typically. You'll notice that this is the entry point, and the initial population needs to be divided among many categories. But when people come in for the first time becoming diabetic, they'll progress down here, and they'll go through these stages of diabetes. We prefer using competing risks models to assess hazards associated with developing end-stage renal disease and developing and dying while a diabetic. And these competing risks analysis are biostatistical models. We analyze them in several different ways collaborating with biostatisticians, and we have published papers on this. And the results of that competing risk analysis were placed directly into this model to capture people's progression. Now, there's some strengths of that. There's some weaknesses of that, and I'll talk about that a little bit, but I want to give an overview. Fundamentally, we have a statistically grounded representation of people's movement through the system, categories of time with diabetes and death. At some point, people reach end-stage renal disease, and then they proceed into a modality where they're delivered dialysis, either peritoneal or hemodialysis. And over time, they switch between those modalities. Those modalities govern factors such as the cost that they exert on the system and the risks associated with developing an infection and hence death. Hemodialysis is associated with these machine care, say 3 times a week to undergo dialysis, whereas peritoneal is based on you're actually carrying around fluid over time within your body that helps with undergoing it internally, so you don't have to go for care. For some of our northern population, we have a population in Canada of Aboriginal peoples who suffer very high rates of diabetes, and we've done much of our work in modeling as well as epidemiological studies looking at the burdens associated with that. In older women, those 55 or older, among people, over half of women have died. And for men, it's upwards of 40%. So talk about a very large fraction of the population. Many of the individuals in that population, though certainly not all, live in northern communities where literally to go to a dialysis center takes 3 hours drive in a taxi, and because they don't have a private car in some cases and in many cases. And so in this case, peritoneal dialysis can confer significant benefits for quality of life because they can undergo care at home. In any case, among these dialysis modalities, we were accumulating cost information as well as health status information. And people over time could die. People over time could receive a transplant as governed by that discrete event component of the model we saw earlier, that long waiting list associated with assessment, associated with waiting for the kidney, and associated with delivery of the kidney. They were delivered a transplant, and then we distinguished between successive periods with a transplant in order to recognize the different risks, different health risks, and different costs associated with those different phases of living with a transplant. So there can be graft failure, where the transplant fails, potentially due to immunological or infection issues, and other cases where a person actually passes away during that time. In any case, the costs tend to be much higher early on than later. Early on, there may be care required in a hospital, and later on, not so. And a kidney can last decades if one's careful. So here we have this agent-based model characterizing these individuals who are in this subset of the population who really need detailed simulation, and then this DES model capturing certain set of those individuals who are currently circulating under care processes. So this would be for the care process side. So this is ABM, and some of these are further in the DES representation of this model. Undertaking it in this fashion is partly motivated by immediate concerns. Certain things were cleaner to express in this way. You could capture the dynamics of the DES model. You could capture resource availability, and you could capture people's waiting times, et cetera, using an agent-based model itself. But it was crisper to characterize them using a DES model. It's much more natural fit to the whole issues of capturing resource limitations and wait queues, and to be able to examine alternatives for those. If we had more surgeons available, if we had more operating theaters, if we had more a stronger stream of kidneys, to be able to address those issues, a DES model was a more natural tool. So we examined that in the context of DES. Okay. Interestingly, in AnyLogic, it took a little bit more finesse than we thought to represent this issue of availability of kidneys, arrival of kidneys. I thought that would be a very routine issue in representing it, but it's not, because kidneys, once implanted, are no longer returned to the pool. You take in a kidney, use it for some time, you don't seize it, release it, and it goes back to a pool. Instead, it's something that once you take it, it stays with you. And representing that in AnyLogic required a little bit more mechanism than we had anticipated. So it was still cleaner than doing it in an ABM model, but it required these mechanisms down here in the lower right. And it's a good lesson. If you're dealing with these kind of consumable resources rather than resources that are persistent and get placed back into the system, you'll handle those differently in AnyLogic. Okay, so here we have these sort of kidney sources for deceased donor and living donor transplant. So this model was recommended by several features. Again, we could have done an agent-based model for the whole thing, but it was much more natural to do this part with the caregiving behavior in DES because of the presence of resource limitations and waiting times, et cetera. And it was much more parsimonious computationally, it required less computational burden to implement most of the population in a system dynamics model. We already had a model at hand, and we didn't really need the whole population in an agent-based model when our interests were quite squarely on just a small subset of it, this 15%. Okay, so it came out. The way in which it was implemented was fairly straightforward. We actually imported a Vensim model into AnyLogic for this process. It was a highly subscripted Vensim model for those who understand that terminology. For those who aren't familiar with it, within aggregate models, the ways in which we capture heterogeneity, variation between individuals, is we conceptually disaggregate a model, so we make separate copies of a stock conceptually. But the way in which that's done at a practical level is we introduce subscripts. So there might be a stock of people who are normal and underweight, and we lend it subscripts to represent people of different ages. In this case, I think there were 17 age categories, different sexes, in this case 2, and different ethnicity categories, in this case 2 as well. And so age, sex, ethnicity, and may have been an additional category as well. In any case, each stock here was subscripted by these. And importing the Vensim model into AnyLogic was pretty straightforward, but it caused a little bit of issues with some of the subscripts that we fixed up. And we've done this for several larger Vensim models that are highly subscripted, and we found, about the order of 1 day of fix-up. One thing as a warning, going to import things into AnyLogic. Be aware that while they'll be logically imported, the appearance is often really distorted, and you've got to put in the time at some point to clean up the appearance. And if you look at the system dynamics model here, it is adversely affected in the extreme by this, and I'll show you what it looks like. So this is how it's imported in a most aesthetically displeasing fashion. We just need to take a couple hours and sort of prettify it, but don't expect aesthetics from the import process. Yes.
Technological plug is very important to it. In network analysis,
yeah.
There are tools to place nodes.
Yep.
So that you minimize the connections.
Yep.
It sure would be nice if there could be some automated way to do that with SD diagrams.
Yeah, I've thought about doing that before. It's interesting, and I think it would be a really good student for someone in computer science from human-computer interaction or usability area. A doctoral dissertation could be done in that where they really nail the problem.
It would sure be nice.
Yeah.
Yeah.
But you'd want to take into account the specific character. It's not. You wouldn't want to just represent as abstract vertices and nodes. You could get some mileage out of that, but you'd want to take into account the specific kind of representational conventions associated with system dynamics, which, put preference to representing sort of aging chains in a straight way. So that's a good point.
Yeah, that would be so valuable. I'd love to help anyone I can with that.
Very interesting, yeah.
Yeah.
As a result, not just a dissertation.
Oh, yeah. Well, we build our own software for modeling, and I mentioned that agent-based modeling software that we're creating and has gotten some distance, and so those sort of features could be built into existing system. I actually think Vensim as a company would put quite a bit of interest in that, and AnyLogic might as well. If you could say, like, clean up my model.
Yeah.
And it would go clean it up. That would be a kind of nice contribution.
As a user.
Yes.
That's one of the hugest things I wish it could do.
Yeah.
Smartly.
Nice. Okay. Any other questions about this model? Yes.
How do you inject people from system dynamics part to the
agent-based
part?
Good. Let's take a look at that. It's a fairly conceptually straightforward process, but it's a little bit archaic in its representation. And I'm going to go find this now. The basic deal here is, I'll describe it at a conceptual level, and we may go look at some of the code for it. So at a conceptual level, people are coming out of this model at certain defined points. I'm simplifying things here. There's actually several flows out, but they lead to agents with different characteristics. And the basic gist of it is we figure out how many people have flowed out. And as I recall that, we do that through having a stock, an actual stock that leaves this. And the key thing we take advantage of is, this is a strategy that I formulated. I believe it was the final one settled on. I remember there were competing ideas, but I think this is the final one settled on. You basically have a stock into which these people flow, and you periodically, and I think I can't remember, every day or 2 days or whatever, you periodically go to that stock and you say, okay, are there one or more people in the stock? Okay, and if so, you basically, at a conceptual level, you take a person out of that stock, you decrement it by one person, and you create an agent with the requisite characteristics. So this stock here is going to be subscripted by, say, age, sex, ethnicity, and you will then create a person with those characteristics, age, sex, ethnicity, as an agent.
And you have just those 3 dimensions for each person, because in system dynamics you will have a exponential explosion with the number of stuff. If you have too many dimensions per...
Correct. So the system dynamics model, this is exactly correct. As you add a new dichotomous dimension into system dynamics, let's suppose you add sex into a model which doesn't have it, then it blows up the size of the model by 2, right there, and across the model. It's not a localized operation like it is adding a parameter in an agent-based model. You add a new parameter in, it affects that little piece of the model, but in a system dynamics model, it affects all the stocks, across there, and so we have a number of stocks. I think it's 3 or 4 within the model, and conceptually, therefore, each stock is we have several layers of each stock, right? Sort of corresponding to people of different ages, sexes, ethnicities. And for each of those layers, we do this operation. So if there's more than one person in it, we go and create the person with the requisite characteristics. Now, it's a little bit more textured than that, I think, because I think they're given an exact age. Yes, they're given an exact age drawn from a distribution for that age category that's empirically based. So let's suppose that they're in the 75 to 79 age category. You don't want to treat that as uniformly distributed, right? There's more 74-year-olds than there are 79-year-olds. And so we draw from an empirical distribution, which we have about how that age category is distributed, okay? And we know their sex, we know their ethnic category, and we create an agent with those characteristics. Now, having them as an agent then gives us all sorts of flexibility because we could further keep track now of their history information as they go through their encounters with the healthcare system, the time of diagnosis, all those sorts of things. So it affords us capacity for extra precision down the road. Now, one thing that this strategy does not allow us to capture directly is for the general population, we're not capturing certain characteristics that I'd ideally like to, rural versus urban, or better yet, where are they living in the province? Because that could affect the need for dialysis centers in different areas of the province, right? That's of keen interest, but that was something that by this hybrid division, by not characterizing this population here, we got a lot faster execution because we're just representing a smaller group of people, but we sacrificed the ability to capture that aspect of context. Similarly, aspects of their family structure and maybe being able to take into account risks associated with other members of the family who may have dialysis or what have you. So the point is, these things always have trade-offs, but this is one type of division that can work very well, and it's surprisingly easy to capture. So a stock in any logic is so if we were to do this would be budding model, right? We're bud off agents, and if we were to do this here we have agents. This is a person agent, hybrid model, maybe we should call it. So I'll call it a budding hybrid model. Budding hybrid SDABL. And here, in person, I'm going to lend them. You don't have to follow along this. In fact, I'd encourage you not to because we're very close for lunch here. But you could take this. Here they are. They're given a nice appearance. And then up here, I'll put in stocks and flows. So adding stocks and flows to these models, you should be aware, it's very straightforward. Can drag in, a stock of, this would be, non-diabetics conceptually, right? Non-diabetics and then diabetics, right? And suppose we want to represent those at that stage of care. And then we put in place a flow, and this is becoming, diagnosis with diabetes, right? And give me that. There we go. Oh, come on. Okay, boom. and then there we go. Okay, and suppose this is just driven at some, right here, this is a system dynamics model, and we could specify, remember we specify the value formulas for the flows, so we'll give, maybe it will be 10 people per month, right? We'll make this month or something like that. For diabetics here, we have people coming in, and the thing that you can do, the basic crux of the issue that you asked about the mechanism, is you have an event going off, say every 0.03 months. Oh, what am I doing? So, but this is the individuation event, the budding event, which will bud these people off as individuals. It will go off with a timeout and cyclic every 0.0 time, so every day. Okay. Can we say every one? Hey, nice. Okay. So this goes off every day, and then it's sort of time to make the donuts. So we're going to get the number of whole people here in the diabetic state. So int count agents to be created, right? And this will be floor. We'll round down. I think this returns a double, so we're going to have to cast it to an int. We're going to have to turn it into an integer, but the floor of the count of diabetics, diabetes. Now, does floor take a double or it takes a float? Don't tell me. Okay, yeah, it takes a double. Okay, happy. Okay, so this is the count of agents to be created, right? And then we're going to reduce the number of diabetics. Well, here you go. Minus equals. Who was at the Java tutorial could tell us what that does. What does minus equal do? Okay? Yeah, it sets diabetes to be diabetes minus this thing, right? Okay, that's good. And then we're going to need to add these people to the population. So let's go create a population here. Here we go, population. And we're going to create a population of agents of size initially 0. Okay? And let's lay them out. This is main. Let's lay them out random. Oh, we're going to add them into the population. How do we got to lay them out? Anyone remember? Got to lay them out through this. Ooh, uniform 0 to 500. Uniform 0 to 500. We learned that lesson. Okay, great. And now we're going to create that many people, right? Just to make it terribly obvious, let me now go loop through for int I equals 0, I less than this number. We're going to count up 1, 0, 1, 2, 3. And for each person, we're going to create them. How do we create them? What do I type? Add underbar population. We're going to add them in. Okay? Let's go see if this works. Okay, 6 error on S. Okay, there we go. Okay. Okay, not delete my S? Oh, wow. Okay. Did I do it again? What am I pressing? Oh, I'm pressing Control Save. That's what it is. Okay. Okay, happy. Okay. So here these people are coming in, and there they are. At any one time, let's pause this model. Here's one person awaiting creation, right? So they're coming in. Let's go slow. Okay, see that? It keeps them getting up above 1. It looks like a jagged sawtooth. Look at this. Right? It's hey, oh, come on. You could scale better than that. Okay. Fine. In any case, the point is you can hear we've budded off agents. We've individuated people once they reach a certain progression in their healthcare state. Is that helpful? That's the essence of it. And of course, there's a lot more bookkeeping when the stock is subscripted according to different dimensions. We just create someone with those characteristics. Works great. Yeah. Periodically. Yeah. It would be nice if somehow it would.
But like, could you have a function
Right.
that once the count in the stock is incremented, like create a variable in the stock so that once the count is incremented, every single time the count is incremented.
Beautiful. Beautiful idea. Yeah, let's put in place the Maria event. Okay? I like this idea a great deal. And this might actually work. This is the Maria Bud event. Well, okay, that's, you don't want it probably. So this will be conditional budding. Okay, this budding there. Okay, so this will be a trigger type condition. The condition will be what? Diabetes greater than 1. And rather than this going off, let's set this to be ignored. So this will no longer be used. By the way, that's a pretty handy feature to say ignore that. Conditional budding. Once it's greater than 1, we'll go do this. Well, we're subtracting. So we get the number to be created. If it's like 1.3, it'll be one person to create. And then we subtract off 1 because we're creating one person and we create them. So here I'm going to run it, and this will, I think, be it's not. Okay. You're right. It's and I would have expected this to, because normally the conditions based on these things should go off. I've got to double check on that. I'm not sure why that's not. I would have expected that to work just fine, actually. So that's weird to me. This is just the second time this morning conditions have not behaved as expected. Oh well, I think it's a beautiful idea, and I think we should be able to do it. But let's re-enable this one. And I know what you mean. You could do this in an adaptive way, because if it's rising quickly, you might want to do it more than once every day, right? You might want to do it more frequently or whatever. But in any case, that's the basic essence of it. You have people flowing in. Once they've reached a certain critical mass, you turn them into individual agents. So to be clear, let me parse this code for you, and then we'll go to lunch. So this code, the first thing we do is we basically get the count of agents to create as an integer by taking the floor, meaning the integer part of the number of diabetics. So if there's listed in the stock as 1.3 diabetics, we take 1. If there's in the stock 24.2, we take 24, right? If there's 0.3, we take 0. Okay, now we say, okay, we're going to be creating those. Maybe it will be clearer conceptually. As a software engineer, I would say this thing should probably go last. Once we've created them, then we'll subtract it off. We'll sort of say, okay, we no longer need them there. No, but I remembered the number and the count of agents to be created here. Yeah. Either way you refer to it, it's that. This diabetes is a bit more explicit, but it's the same thing. I see what. That's interesting. I see what you're saying with the condition. That's interesting. I'll come back. I'll examine that separately. But here we get the number to be created. We go through and we loop and we add them to the population. And then since we've created 5 agents, and we say we had 5.3 agents in the stock, that's what this is. We said, okay, there are 5 agents to be created. We create each of these 5 agents. That's what this loop does, 1, 2, 3, 4, 5. And then we subtract the count in the stock, 5.3, we subtract off 5 to get 0.8. Does that make sense? Yeah. Okay, great. So far be it for me to stand between you and lunch. I will